So, in the world of complex dynamics, we have these beautiful, predictable structures. But what happens when you introduce a specific kind of mathematical tweak, a non-holomorphic perturbation? Well, recent research showed it can completely shatter one of these structures, the Feigenbaum-Borel singularity, leaving just chaos in its wake. The big question then was, is there any order left at all? The previous paper, paper 27, actually found a boundary for this chaos using something called the law of the iterated logarithm. But to prove it, they had to use a deliberately oversized, super-safe constant.
Okay, so let's talk about this number, 3.0. This was the yardstick from the last paper, a safe, guaranteed upper bound on just how wild the fluctuations in this new chaotic system could get. You can think of it like setting guardrails on a highway, but making the road a mile wide just to be absolutely positively sure no one could ever drive off. It was rigorously proven to work, no doubt about it.
But here's the thing. Safe is not the same as precise. That constant was intentionally conservative. And that leads directly to the question that drives this entire paper. Just how loose is that bound? What is the true, sharp limit that perfectly describes this system's real behavior? And, how much smaller could it actually be?
To get to the bottom of that, here's our game plan. We'll start with that loose bound, get a feel for the orbit and the law governing it, and then walk through the really cool theory that connects this chaos to random walks. After that, we'll dive into the numerical experiment that calibrates the true constant, and finally, we'll see where this all fits in the bigger research picture.
All right, first things first. Before we can really appreciate the discovery in this paper, we need to quickly get reacquainted with the system we're studying and the mathematical law that's supposed to tame its behavior.
So the system we're dealing with is called the bird map. Now, a really key feature, which was proven in earlier work, is that it has this clean separation. The vertical component of the system's orbit, that's the y part, it evolves entirely on its own. It's completely unaffected by the horizontal x part. And that's perfect for us because it gives us this pure, isolated, one-dimensional chaotic system to really dig into.
And the rule that governs these fluctuations, that's the law of the iterated logarithm, or the LIL. To put it simply, for systems like this, ergodic ones, where the long-term average behavior is the same no matter where you start, the LIL tells you exactly how fast the fluctuations can grow. It's like it draws a perfectly sharp envelope around the chaos, defining its absolute outer limits with total mathematical precision. So the huge takeaway from paper 27 was that this incredibly powerful law did, in fact, apply to the bird map orbit. But, and this is the big but, to guarantee that it held true, they used that one-size-fits-all constant, c equals 3.0. It was a provably correct bound, sure, but it wasn't tailored to the specific dynamics of this system. It was a gate, not a glove.
Now we get to the really cool theoretical part. How do you even build a bridge from a general, safe constant to a specific sharp one? Well, the key is to connect the deterministic chaos of our map to the very well-understood world of random walks.
This slide lays out the whole argument in 4 beautiful steps. First, our system is what's known as an expanding map. It's always stretching things out. Because of that, the system forgets its starting point incredibly fast. This is a property called fast mixing. And this fast mixing is the secret ingredient that lets us use a super powerful tool called the almost sure invariance principle, or ASIP. And ASIP, well, that's what guarantees that a perfectly sharp constant for our system has to exist, even before we have a clue what its value is. Think of ASIP as a kind of deep mathematical translator. It proves that for fast mixing systems like the one we have here, the long-run behavior of our deterministic orbit is statistically indistinguishable from a truly random process, like Brownian motion. This is the bridge. It's because of foundational work by mathematicians like Guezel, Melbourne, and Nickel that we can take the sharp, known rules from the world of randomness and just apply them directly to our chaotic system.
And this is a really vital distinction. Theory gives us mathematical certainty that a perfectly sharp constant, C star, exists. That's a huge deal. But what theory doesn't do is tell us its value. And that's the whole contribution of this paper, to roll up their sleeves and run the high-precision numerical experiments needed to find out exactly what that number is for the bird map.
So let's get to the main event, the numerical calibration. This is where we go from knowing a number exists in theory to actually having it in our hands. And, this is where we get the punchline that shows just how incredibly conservative that original constant of 3.0 really was.
So how did they do it?
Well, the method was pretty straightforward in concept, but definitely intense to compute. They picked two different ways to observe the system's state, by calculating the hyperbolic tangent and the sine of the y value at every single step. Then they let the orbit run for 1,000,000 iterations for each of these observables and applied a standard statistical tool to figure out the long-run variance. That variance is the key ingredient we need to find our sharp constant.
And here is the core finding of the entire paper, all laid out in one table. On the left, you've got the two different ways they measured the system. Next column, that's our old friend, the safe constant from paper 27, a flat 3.0 for both. But then look at the third column. Those are the new, precisely calculated sharp constants. And that last column, the sharpening factor, the difference is just staggering.
Let's just focus on that first result for a second. For the tan observable, the old bound was 3.0. Simple enough. The new, true, sharp constant is 0.00384. It's a completely different kind of number. It's not even in the same universe. Our understanding of this system's boundary just became 780 times more precise. That original bound wasn't just being a little conservative, it was completely obscuring how incredibly stable this system actually is. Okay, now if you thought that was dramatic, take a look at the sin observable. Again, the old bound was 3.0. The new constant is almost infinitesimal. It's 0.000083. That's 4 zeros after the decimal point before you even get to a number. That is a 36,000-fold sharpening. 36,000. At that point, it's not just a refinement, is it? It's a fundamental change in our entire quantitative understanding. The fluctuations in this system are genuinely astonishingly small. So the real takeaway here is that these results reveal the true scale of the system's fluctuations. And that scale is just orders of magnitude smaller than that safe bound ever suggested. The system is so much more regular than we had any reason to believe before. The paper also does a great job of tying up a few important loose ends. First, these results are robust. If you tweak the system's parameters a bit, the constants don't go flying all over the place. Second, it clarifies why some ways of looking at the system just don't work. The exponential function, for example, can shoot off to infinity, and that breaks a key assumption needed for the whole theory to work. And finally, they noticed a tiny statistical hiccup in the sin data, but they traced it back to a brief temporary pattern, confirming that the system as a whole is still mixing exactly like it's supposed to.
Okay, so let's zoom out. What does finding this number really mean? How does this incredibly sharp new understanding fit into the bigger story of the non-holomorphic fractal series?
When you look at it this way, you see this powerful logical progression. Paper 26 was really about destruction. A known, beautiful structure was erased by a new kind of perturbation. Then paper 27 was about control, establishing a safe, universal boundary on the chaos that was left behind. And now, this paper, paper 28, is all about precision, calibrating the true nature of that behavior and revealing that it's far more constrained than we ever knew. And this leads to a really powerful practical application. These new constants, they aren't just some abstract numbers. They act as a diagnostic fingerprint for this specific chaotic regime. So if you run into a similar system out in the wild, you can calculate these constants. And if they match, that's a really strong indicator that you're dealing with the same underlying dynamics. It's like a quick, compact health check for the system.
This whole work leaves us with a really compelling final thought. The journey from a safe constant of 3.0 to a sharp one that's 36,000 times smaller revealed this incredible hidden layer of precision. And it just makes you wonder, right? What other chaotic systems, in physics, in biology, maybe even in economics, are we currently describing with these safe but loose bounds? And what vast, undiscovered levels of precision might be hiding there, just waiting for someone to go and measure them?